All right, so hello. Thank you so much for joining us today for our webinar, How to Get More Consistent Data in Composites Testing. My name is Denise Enck. I'm the Senior Coordinator here at ACMA for events, and I'll be moderating the webinar. So I have a few quick notes before we get started. Please note that all participants are muted to limit background noise. If you have questions at any time, at the bottom on your toolbar, you will find a chat box or the Q&A. You're welcome to enter those questions there. In addition, following our presentation, we will have some time for the Q&A. The last thing is you will receive a link for this webinar in the next 48 hours, and you'll have instructions in that email on how to access and view the recording. So I am excited to introduce you today to a company that's at the forefront of cutting-edge materials testing technology, Instron. They were founded in 1946 and headquartered in Norwood, Massachusetts. Instron manufactures a wide range of advanced testing equipment used by researchers, engineers, and quality control managers across industries, academia, and government. Instron is the go-to partner for evaluating the mechanical properties and performances of raw materials, components, and finished products. Their comprehensive product portfolio and depth of technical knowledge allow customers to tackle even the most complex materials challenges. In today's webinar, you will learn more about how Instron can empower your work. Joining us today to present is Ashley Davis. She is a mechanical engineer with a diverse background, having worked in quality automation, business development, and now in applications engineering. As an applications engineer at Instron, her primary focus is on static high force testing for composites and other high strength material applications. We also have joining us Stephan Botzki. He has a background in mechanics and data analysis. As a senior applications engineer at Instron, Stephan's primary focus centers on static high force testing for composites and other high strength material applications. He is a voting member and recording secretary for the ASTM D30 Committee focused on composite materials. Ashley and Stephan, thank you for being here, and I'll turn it over to you now.
Thank you very much, Denise. Welcome, everybody, to our webinar today. I'm going to look at the agenda first here. So we're going to start out with some composite testing overview, so just a little bit on the material itself. Then we're going to look at specimen preparation, test equipment considerations, specimen alignment, temperature testing, and then a couple random various tips and tricks that you can follow to get more consistent data in your test results. Okay, so we're gonna start out with a little bit on the material itself. So today's focus is on testing composite laminates made from carbon fiber reinforced plastics. That's what we're mainly going to focus on today. And the laminates and coupons that we're talking about, they're down here in the bottom of the test pyramid, where we're interested in testing for quality control, research and development purposes, and just in general establishing material databases that then engineers can use. Composites in general are a complex material on a macro and also on a micro level. They're considered anisotropic, which means that their strength, for example, is dependent on the direction from where a load is applied to them. So if we consider this simplified model down here on the left corner, where all of the fibers are aligned in direction number 1, that's also the same direction if you were to apply a load there, where the coupon has its highest strength and highest modulus reading in that direction. So if you were to apply a tensile load or a compressive load in that direction, that will be its strongest direction. It will be much weaker in direction number 2 or in the through thickness direction number 3. So because they're generally considered anisotropic, they require multiple types of tests to fully determine their properties. So you need to do a lot of tension testing in all the different directions. You need to do compression and shear and flex testing with all the different combinations of directions. The same is true for the modulus of any given specimen. So the strain also needs to be determined in all the directions, as well as the relationship between the axial and the transverse strain in the different combination, as you can see down there. And then on a micro level, we're interested in things like the fracture toughness of the laminate, as well as the compression after impact strength for aerospace applications, for example, and then also filled hole, open hole tests, depending on how, how the end application, how the material is going to be used in the end application. We also need to simulate a lot of times different temperatures and humidity levels because they also affect the properties. And that means that there's a lot of different specimens, a lot of different test types, a lot of different equipment that you have to use, and a lot of measurements that you need to take that all need to be properly controlled. Otherwise, it will lead you to inconsistencies in your testing data. Okay, so we're going to move now into the specimen preparation section here in our presentation. And right up front, I'm going to tell you that we at Instron don't make composite test specimens. So we're typically at the mercy of our customers when it's, when we get specimens sent in from them to be tested for troubleshooting or other purposes, or we need to buy them somewhere, or we work with some of our partners. For example, the University of Utah is a great partner of ours that has supplied us with test specimens in the past. So we don't make composites, but we test them a lot. And also in the testing standards, there's a lot of information on specimen preparation. So this is where I got this information from many various different testing standards. Okay, so we're going to start out. So first of all, of course, if you have damaged specimens, it will affect your strength and your modulus. And depending on where the damages are coming from, you might have a couple outliers here and there that will definitely affect the consistency of your testing data. The same is true for inaccurate fiber alignment, which is also much harder to figure out, but nonetheless there are things in the testing standards practices that you can use to find out if your alignment is in good condition, if it's within the tolerances that the standards allow you. You also need to have the right ratio of gauge length to thickness to prevent buckling in compression tests, for example. And again, testing standards give you good guidance on what ratios to use, or they have standardized specimens that are known to work well. So you need to make sure if you need to kind of like make adjustments to yours, then make sure that the ratio works. Otherwise, buckling will of course affect your strength and especially your strain and therefore modulus readings. On the other end, if you're doing tension tests, you should consider to maximize the length of your specimens beyond the minimum length requirements in the standards. There's typically, from what I've seen, not like a maximum length. There's typically a minimum length. And now if you think about it, if you maximize that, any kind of bending arrows that could be introduced from the grips, for example, would be minimized the longer your specimen is, the less of an effect that certain amount of arrow will have, right? So if you just increase the length, that can help you with that. If you're doing end loading tests where your specimen, gets end loaded like ASTM D695, or you have a combined loading test like the ASTM D6641, you need to make sure that the ends of your specimens are flat and parallel, because that's obviously one of the major ways here in the combined loading, for example, how you introduce the load. So if your ends are not flat, you're going to have an uneven load introduction into your specimen. You might also have failures where you did not want them. So you don't want them to fail here at the ends. The edges of your specimens also need to be parallel and flat within the specified tolerances of the testing standards. And lastly, on this slide here, make sure that you label your specimens so that if you need to check back for any kind of errors, you can trace back to the raw material where your specimens came from. If you make specimens, you should consider to mold them individually, or if you have to, you will cut them from a plate. And if you cut them from a plate, you need to make sure that you avoid any kind of notches or undercuts or rough and uneven surfaces. Or you could also have delaminations, which could be caused by any kind of inappropriate machining methods. So this is actually when you're actually milling the composites. So be really careful with that. And then typical processes that have been used in the past successfully are, for example, water lubricated precision sawing, milling, or grinding. And also diamond tooling is very effective for many, many material systems. There's also testing standards that focus on this. So for example, the ASTM D5687, which is for preparation of flat composite panels, and then also processing guidelines for the specimen preparation specifically. So you'll see some of these standards referenced in the testing standards. So a testing standard will reference one of these here, for example. In ISO, for example, you got the 1268, which is the method for producing test plates and molding of prepregs. And then also in the testing standards themselves, for example, the ISO 527-5 for unidirectional fiber reinforced plastics has a lot of information on how to properly prepare your test specimens and tolerances and so on. Now, one question when we talk about tabbing now is, are you actually achieving the required failure mode or modes within the testing standard? So if you are having a successful test where the specimen fails in the gauge section and you have the right type of failure mode, you probably wouldn't even want to consider any tabbing because you're doing what the testing standard is asking and you're achieving the right results. Now, if you have any kind of grip failures or you're outside of the gauge section where the majority of your failures happen, then that is a time to really think about your process and consider using tabs. And what you could start with is something like friction tabs, like emery cloth or sandpaper, which you can use with the rough side is usually what has been successful for me personally. If you use the rough side of the sandpaper, you put that around your test specimen ends, and then you clamp onto that with your grips. That has definitely helped me personally to achieve the right failure modes and also get them in the gauge section of the specimen. Now, sometimes friction tabs alone are not sufficient, and then you need to really have bonded tabs that are basically glued to your test specimen with an adhesive. And tabbing itself in general is kind of an art, and it definitely can have an influence on your testing data, on the consistency of your data. So just like the specimen preparation itself, where you machine the coupon, you need to take the same care with your tabs and also follow the tolerances within the testing standards. So that's what you should do when you look at how to tab, what kind of tolerances to follow. And you also need to make sure, they're flat and parallel. You use precision grinding methods after they've been bonded. And typical materials that we see there used are glass fiber reinforced plastics bonded to typical CFRP coupons. I've seen different types of metals like steel or aluminum. And I've also seen in testing standards that they actually recommend to use the same material that is being tested to be used as tabs as well. A little bit on strain gauges here. Of course, strain gauges can also give you strain anomalies due to either direct gauge disbonding, or you have a potential separation of your leads to the strain gauge, or the surface ply of your specimen is separating. So all of those things obviously are going to affect your strain measurements, and strain gauges are still a lot of tests required to obtain your strain data. You could also have errors in your strain gauge calibration. You got to make, of course, like for example, if you set it up in Blue Hill, you got to make sure that you use the right gauge factor for your strain gauges, and of course, inaccurate placement of the strain gauge itself will also cause you a lot of inconsistencies in your testing data because you're just not reading your strain data in the right orientation. Now let's assume you got your perfectly prepared test specimen. Now you need to measure it as well. So there could be inconsistencies if you are not using the right procedures. You're not always doing it the same way, or that the equipment that you're using is not accurate enough. And again, testing standards typically have sections or reference other standards that focus on measurements that will give you the required tolerances for the equipment that you use, like the micrometers and like kind of what end they need to have where they touch the specimen, and also the accuracy that they need to have. There's in general, if we're looking at composite testing standards like ASTM D3039 or 6641, again, they're very popular. They typically require you to measure the width and the thickness at 3 different locations within the gauge section. And again, that's where we want to have our failure, right? The gauge section of the specimen. So that's also the area where you will do the 3 different measurements for width and thickness, and then you average those, and that will be what you use for your values. There's also software assistance that you can use. You can see that here on the screen, where you can connect a micrometer directly to Blue Hill Universal, and then you measure your specimen, and then either with a click or with a foot pedal, if you prefer that, you can have that data directly being entered into the testing software. That way you can avoid any kind of an error between reading the result and actually entering it. There's also a feature in our software that's called Workflow. You can find it in the Method tab here, and then in the different tabs below, all the way to the right, there's a section called Prompt to Test, which you can activate here with this toggle, which is called Run as Prompted Test. So you toggle that on, and then below you can make different sections of the test. You can see that kind of here in the workflow itself. At those steps, so for example, you start a new sample, or otherwise called batch, right before the test of a specimen, before the analysis, after the test, all those different sections, you can prompt your operators, and you can put little notes or little pictures like you can see here. Up here, you could put any kind of important note or any kind of specific equipment that has to be used. You can use pictures to prompt your operators and guide them through, so they need to click here on the arrows on the bottom here to advance further, make the required entries. And you can remind them, for example, if you're using an extensometer, to make sure that it's the right type that they're using, and that the placement onto the specimen is correct, and that the extensometer is, for example, not crooked, because otherwise that will, of course, give you variation in your strain measurements again, and therefore, of course, inaccuracies. Now we're going to move on to the next section of our presentation, which is on test equipment considerations, from Ashley.
Thank you, Stephan. I first wanted to start out this part of the presentation with this video showing a test on a composite coupon, and this may look familiar to some of you. This is a high-strength unidirectional test specimen, and looking at this violent and abrupt failure type, we can keep that in mind when we're talking about our test equipment. We definitely want to ensure that we are using a stiff machine to be able to handle those high strength materials. Here we actually have data collected when we performed high strength brakes on our latest 6800 series of frames, showing that the bulk of the energy, as shown in Gs, is absorbed in the base of the frame at 145 Gs, followed by the crosshead at 105 Gs, with our critical electrical components and where our motor lives experiencing the lowest amount of Gs during the high energy brake at only 27. This is all influenced by the preloaded bearings, precision ball screws, the solid thick crosshead, the solid base beam, and low stretch drive belts. And ultimately, this leads to superior performance and longevity of our frame. These design considerations are also super important, as we want to keep the testing machine compliance to a minimum, as it does affect the strain rate when we're using crosshead control. Machine compliance can also be influenced by having a simple load string with as few connection pieces as possible. We want to make sure that we're not having over piggybacking within the load string, because we're then just building compliance essentially. And then it's also these design considerations that influence our load string alignment. The 6800 series of frames with either precision manual wedge grips or hydraulic wedge grips actually can pass NADCAP alignment verifications without the need for an additional alignment cell when being used with our standard height of frame or our E1 option of frame. And I'm going to get much deeper into alignment later. We're going to spend some time on that. To keep our frames functioning for the long run, we made some design changes to our floor model systems to improve the ingress protection of those electrical components and where the motor lives, to better deal with all of those carbon fiber debris. We wanted to make sure that we're preventing all of that from getting inside and gunking up, our components. The 6800 series frames were designed with improved ingress ceilings to combat the dust and debris by actually adding a gasket between the rear cover and the base beam and to reduce the gapping that might have been there. And we improved the existing gasket on the front cover. And then on the right, you can actually see on the left side, you can see our previous generation of frames where we had some cabling and a limit rod. So there was actually access points to go into the base of the frame, and those holes can allow for dust and debris. So our engineering team actually removed those completely, so we are completely sealed. And it's simple changes like these that can help strengthen the protection of those components within the frame, which means that we have less time for having to clean and hopefully less servicing. I'm going to spend some time talking about load cells. Instron is really unique in that we're the only global material testing supplier that designs and manufactures its own load cells. And an important point here is the measuring range. You can test down to 1/1000th of the load cell capacity and still meet the accuracy requirements of international standards at 0.5% accuracy. This allows you to conduct testing, which requires high forces. Maybe you're doing tensile or compression tests on coupons, and then also testing for lower force tests, such as interlaminar shear stress testing, without actually having to switch out your load cells. Now, as I said before, we don't want to add more compliance than we need to the frame. So if we don't have to piggyback, we definitely don't want to. All of our load cells are high quality, manufactured using precision machining and construction. And then, as I said before about the frame, high stiffness is important. So our load cells also have high axial and lateral stiffness for load string alignment, as well as reducing that compliance. So next I want to talk about how do we actually read the specifications of our Instron load cells. On our product sheets, on Instron's product sheets, we state that the load measurement specification as a percent of reading down to a fraction of a load cell's capacity. So for example, this will read as, for our 6800 series, we state that load cells on these frames have an accuracy of plus or minus 0.5% reading down to 1/1000th of the capacity of the load cell of our 2580 load cells. So essentially, our percent of reading tells us the level of accuracy at a specific force measurement based on the usable range of a verified load cell. And we'll get into some examples on real life load cells. So if we have a 10 kilonewton load cell, what is our accuracy actually at 1 kilonewton? With an accuracy rating of that plus or minus 0.5%, this would mean our actual value at 1 kilonewton is guaranteed to be anywhere between 995 newtons and 1005 newtons. So that's our accuracy. What is our range? How do we determine that? Our usable range are the upper and lower limits of the forces that a load cell can be used to measure while meeting that guaranteed accuracy rating. So this is represented as that fraction. So we read plus or minus 0.5% down to 1/1000th. The 1/1000th is the key phrase here. So 1/1000th of 10 kilonewtons is 10 newtons. Our usable range, where we guarantee that plus or minus 0.5% accuracy, is 10 newtons to 10 kilonewtons. Anything outside of that would not meet the guaranteed accuracy rating and should not be used. Let's look at how this compares to other suppliers. On the left, we show the graph for Instron as the percent of reading. And then on the right, we show the graph for load cell accuracy as a percent of full scale. The distinction here is that when we're doing percent of reading on the left, the error actually scales with the force reading. So as we have a higher value, our error is going to be a little bit higher. With accuracy as a percent of full scale, that error is constant and becomes much more pronounced at those smaller load readings. So it might be 100 newtons, but it's going to be 100 newtons upper and lower. We'll do another example. So we have an Instron frame, 50 kilonewtons. Its accuracy of plus or minus 0.05% of reading throughout the entire range. And then our other supplier with a 50 kilonewton load cell, an accuracy of plus or minus 0.1% of full scale. So if we actually pull up those graphs again, we'll start by looking at 50 kilonewtons on the Instron frame. 0.5% error at 50 kilonewtons is 250 newtons, which is a little bigger than what it would be on the other supplier. But if we're using this system to do low force testing and we are reading a value of 50 newtons, on the Instron frame, we have that 0.5% error at 50 newtons as plus or minus 0.25 newtons. If we go over to the other supplier, at a 50 Newton rating, we have 100% error at with plus or minus 50 Newtons. So we're, although we might be better at higher values, you could say, this is huge if you are trying to do a lower force test on the same load cell. And it's very likely you won't actually be within the range of the standard at these lower values. So many testing standards do refer to ASTM E4 or ISO 7500-1 to define the accuracy requirement. For instance, here we say that ASTM E4 specifies the machine needs to be accurate to 1% of reading over a verified range. And this is what we call our usable range. We use that percent of reading to meet the standard of E4. If we pull up those frames again and we compare the usable ranges within E4 of Instron versus the other supplier, Instron's usable range goes all the way down to 50 newtons, while the other supplier's usable range goes down to only 5 kilonewtons. This means if you want to do anything below 5 kilonewtons, you're going to need to purchase additional load cells, which is going to increase your expenses and increase complexity. Each load cell is going to need to be calibrated, maintained, and stored safely, as well as piggybacked onto that system. We always do recommend to check with your standards to ensure compliance, and I do recommend checking out the reference video that our colleague Sammy Sadler made regarding this topic, which goes into it even more in depth. So machine robustness and reliability regarding calibration. This is another consideration that we take. Another unique strength that sets Instron apart is that we have our own deadweight stack here in Norwood, Massachusetts, which is actually used for all of our calibration cells that our service engineers use on site when they're calibrating your own load cells. And in addition to that, you're also going to need to consider your strain devices and regular calibrations of them. Our calibration procedures are fully compliant with ISO IEC 17025 and provide assurance that your test data is valid and your processes are properly controlled. Talking another thing within Blue Hill Universal, your operators may have to frequently change the test setup with different fixturing. You know, maybe you're doing tensile tests, piggybacking compression tests. All of these might have different crosshead positions within the frame. A helpful feature within Blue Hill to deal with these different setups and at the same time reduce variability of your starting crosshead position is auto positioning. Auto positioning makes use of an absolute encoder to configure fixtures for consistent setup. You can save the fixtures within Blue Hill to their correct separation in the test method, and then you let the software do the work to figure out where the crosshead should be, rather than eyeballing the crosshead when you're doing that initial setup the first time. Visual reminders show operators what their fixtures should look like and warn them where the crosshead's going to go before it adjusts. And you can see an example on the screen of what the operator would see when they're setting that up, but we do also have a little video that we can go to, which shows it a little bit better. So the operator has these 10 kilonewton pneumatic grips. When she opens the method, it indicates where the crosshead position will be, as well as shows the images of what the load string should look like. Press this go. And then it's always going to be in that same initial position. As I said, you don't need to eyeball it. It's just going to save that for you. So next, I'm going to talk about alignment and why alignment is so important. So there are two main types of misalignment that we can experience within our load string. The first is that of angularity errors. This is where our upper grip versus our lower grip might be at a different angle, causing a bending moment. This is going to cause a positive tensile strain on one side of our specimen, indicated in blue, and then a compressive negative strain on the other side of our specimen, shown in orange. The other type of error that we can have is concentricity, where our upper grip and lower grip are not concentric with one another. And this actually creates more of an S-type bending moment within our specimen. So we have regions of positive and negative strain, and this is before we've even started the test. So we've loaded our specimen and we've already created these pre-stresses, these pre-strains to the specimen, essentially damaging the specimen before we've even gotten good data. And I want to talk about next why that's so important. Why is it so important that we're not pre-damaging that specimen? I'm going to talk a little bit about metals. So if we show a typical stress strain curve for a metal specimen, and if that metal is misaligned, so you have tension, compression occurring on the specimen, that metal is going to yield on that one side of the specimen before it does on the other side, but it is going to continue elongating, essentially carrying that load, and show that typical stress strain curve going from the elastic region to plastic. And as I said, even if you yield and carry that load, the ultimate tensile strength is ultimately going to be the same. Your modulus and yield will likely be different, but the important thing is that the specimen can kind of make up for the misalignment and continue to carry that load fully. If we compare that to a composite specimen, if we're misaligned, composites are particularly sensitive because they generally are brittle and have low strain. For example, you might have a thermoset resin-based composite in aerospace. Your fibers are going to be very brittle. And if you've loaded it and it already has a pre-stress and those fibers have began to break before the test even starts, we've essentially lost the strength of the specimen. When you have those first fiber breaks, you're going to essentially have a successive rapid failure of the whole specimen. It can't handle carrying that load and redistributing that load like the metal specimen can. This is ultimately going to influence our ultimate tensile strength as well as our modulus and stress strain results of the specimen. There is no plastic region and we can't redistribute. So this is not ideal to be preemptively loading and having something that's misaligned. We did some tests a couple years ago where we purposefully tested coupons in a misaligned load string. So here we had an instance where we had grips in the frame, but the grips were not aligned using any kind of like secondary alignment feature. And there was bending moment occurring within the preloaded specimens at about 26% bending moment. In the bottom, what happened was that the load string was then aligned properly using an Align Pro fixture as well as software, which I'll show in a couple slides. And essentially, that got the initial bending moment of the specimen to 5%. So we went from a 26% initial bending moment to 5% initial bending moment. We can clearly see in the upper graph that there's a lot of inconsistency. We have essentially some rough stress strain curves and a wide distribution. In our lower graph, we can see that we have a less distribution throughout the curves. They're much cleaner. And we actually had a 6% increase in ultimate tensile strength when we did the alignment properly. This might sound like a small number, but that could be the difference in quality control environments that allow shipments or even getting business versus a competitor. In areas like aerospace, including which involves NADCAP, they mandate proper alignment. So for metals, they essentially say 10% alignment for ductile, 8% for non-ductile, and 5% for cyclic. For NADCAP for composites, they indicate that the bending moment cannot be more than 8% upon initial loading. And as I said before, the lower graph was average of 5%. There is additional information on our website regarding this testing via the white paper, so I recommend you check that out. So then how do we achieve and verify the good alignment? First thing, I already talked about this. We ideally want that stiff testing machine with the high precision design and build. It helps with longevity as well as alignment. We want to use precision grips that are wedge acting and symmetric, which can allow for testing in ambient and temperature environments, as well as allow us to piggyback other fixtures, like if we were to do compression testing. We can introduce the alignment fixture. This is our Align Pro, which allows adjustments of the angularity and concentricity while under load. It sits in between the crosshead and the load cell. You essentially get it adjusted by service, and then you forget it. And that should be good for the year. This does pair with our service products, which includes the accredited alignment verification using standard or custom strain gauge specimens. So we can report out the bending moment in the load strings using that Align Pro software. I want to talk a little more about gripping. It's no good having a stiff, well-aligned load string if our grips are not repeatable. We need very repeatable grips. The characteristics of the grips required typically. We always recommend a moving body grip, as shown in the animation in the bottom left. And in the middle here, we have an example of a moving body manual grip, which is actuated by a hand crank. And these are our precision manual wedge body grips. The moving body means that the faces move horizontally. The faces don't move vertically at all related to the specimen. So we're always providing consistent side loading clamping on a specimen. And we don't cause any kind of initial compressive or tensile load in the coupon, which again could cause any kind of like pre-breaks. The other thing is that the symmetrical wedge pocket, and what I mean by that is like symmetrical front to back, that controls the alignment of the jaw face, and the jaw faces are always looking to meet on the center line of the testing machine. And then front to back symmetrical body. Also, if we have a grip where it has like a back feature, that means it is technically heavier in the back and can cause a bending moment when you load that specimen. So we want to make sure that we have that front to back symmetry. And then just like general grip tips that we have, definitely preload your load string. If you're testing with a 1 kilonewton load cell and setup up to 600 kilonewton load cell and load string setup, you want to make sure that your load string is preloaded. Our machines, typically with the hydraulic and precision wedge grips, already come preloaded and should not be removed. We recommend using hydraulic wedge grips as it does provide repeatable initial clamping every single time. In our applications lab, we pretty much exclusively use hydraulic wedge grips. If you are to use mechanical wedge grips, like the precision wedge grips, we do recommend that you use maybe a torque wrench when possible, as you could then have repeatable gripping pressure across different operators. Lastly, with gripping, we need to be able to insert the specimens in the grips accurately and repeatably. It's very simple, but you can have specimen stops on your grips, maybe on the grip body or the jaw face, so your operator is always going to install in the same location. And honestly, it just makes it way easier to load into the frame. You're not having to hold your hand up and shaking while you're closing the grips. And on the left, you can see kind of how a specimen could be misaligned if we were to more so eyeball it. Another grip tip that we have is check your jaw faces on a regular basis for damages, and make sure that you are center clamping. So we have an example coupon we tested last year for our strain webinar, where we purposefully misaligned the coupon in the grips, and we used our video extensometer and digital image correlation to map the strain map or the stress map during tests. So in the next slide, we have the video of the test actually occurring. And we can see the map changing over the course of the test, with higher concentrations of stress actually in that lower left corner and that upper right corner. So we're not getting even stress strain distribution throughout the specimen. We can see the localized stresses occurring. Ultimately, it's going to fail at that lower jaw face, which is not an appropriate break. And this would be a failed kind of break. With something as simple as the specimen stops, we can hope to avoid this kind of failure. Lastly, I want to talk about alignment and compression. For compression testing, we typically use compression platens, which have the option of a spherical seat. So one platen would need to be spherically seated, typically the upper one, and one would be fixed. You drive the platens together, and once they're perfectly parallel, you lock that spherical seat, and this essentially meets the NADCAP compression alignment requirements. They have hard chrome surfaces to prevent damage, as well as alignment rings to help you locate your fixtures when you're loading. And then there's a variety of composites compression fixtures, and these integrate guidance and alignment in the fixture themselves. Shown here on the left, we have the combined loading and compression fixture, or CLC, and the E-tree compression fixture on the right. Both of these are supplied by Wyoming Tex Fixtures. And these fixtures are designed and manufactured to be laterally stiff, well-guided, with very low machine tolerances, and then they do sit between that pair of compression platens. The guidance and the alignment comes from the fixture itself rather than the machine. As Stephan was talking about before, in terms of our fixtures and our specimens, we do want to make sure that our fixture surface finishes are polished, properly lubricated, and free of any nicks or damages. And then lastly, if we are going to be doing compression testing with bonded strain gauges, there is guidance in ASTM D30 and D6641 that indicates that your percent bending, so if you have a bonded strain gauge on either side, the average of those of the bending moment needs to be less than 10%. And when you're less than 10% upon initial loading, it's okay to use the bonded strain gauges to report out the strain values that you're seeing within the compression test. And again, this is indicated in D3410 and D6641 if you want to check out more about that. So that's it for me. I'm going to pass it back over to Stephan.
Thank you, Ashley. Okay, to finish off, we're going to look at some temperature testing tricks and tips, and then some kind of random things that should help you for consistent data results. Okay, so temperature testing. Our temperature chambers in the software, we do have automated soak time in there, which would then prevent your test from starting before the temperature is reached. So you set a point, and then once that temperature equilibrium has been reached, the test will be automatically started. So that will help you to always start at the same temperatures. There's also auto-tuning controllers, which get you to the set point really quickly, and you should not have to adjust any other parameters with the environmental chambers, as you can see here on the different pictures. It's also integrated so that you can control the chamber from the software directly. And then to the point of load cells. So our load cells are temperature compensated. That should minimize the effects that the temperature has on the force readings, and therefore also help you with your data consistency, because obviously, force is probably one of the most important measurements that you take in, and a lot of calculations are derived from, right, that is one of the major inputs for that, right? So for temperature testing, temperature compensated load cells are very, very, very important. You can also adjust the fan speed if you're testing very, very low force tests to minimize any effects from turbulences within the temperature chamber. Now we're going to look at a few other tips and tricks that you can use. So if you buy a machine from Instron, you would also get the testing software with it. And with the testing software, you get something that is called a test method suite, which for composites here, we're seeing the example here, has a lot of predefined testing methods. So you can see a lot of Airbus standards in here, a lot of ASTM, EN, and ISO standards. The list goes on here beyond what you see on the picture. So you can use these as a starting point and then just kind of make some little tweaks here and there, or have the service engineer, when he's on site, help you to set it up. And you should not have to reinvent the whole wheel. We already have very good templates here that you can use and then build your methods from there. Another very important feature, now let's say you are suffering from data inconsistencies and now you need to kind of chase down where that is coming from. One point where you can start is the revision history feature. So in the software, you can see here we're in the method tab. You have this little icon up here, which with the stop clock and the arrow around. So if you click on that, it will open up what's called the method revision history. And what that shows you is here with the different timestamps and dates, different days and times when things actually happened, when things were changed. So you can see the action itself. You can see what is affected by it, for example, the test rate or the end of test criteria. And then you can see what the new value is that was entered. And you can also see what the previous value was. So you can see, let's say you all of a sudden have inconsistencies from the previous batches you've tested, and you open this up and you might see, okay, the test rate was changed, and then you can change that back and make sure to prevent that going forward. The same is true when you have that, click on that icon here while you are in the test tab of Blue Hill Universal. It will open up what is called the sample revision history, which is very similar to the method, but it's based on the sample. So any kind of entries that have been changed there. So maybe you're reporting you're missing some entries or something changed, you can pull this up and see what has happened in the past. So in general, this will help you to track all the different changes in the method files or the sample files and also in the report files. Helps you to check operator actions during a test and should help you to get more consistency, or if you are experiencing inconsistency, it should help you to chase down where that is coming from. Should also increase your audit confidence and save you time and money, hopefully, if you do have to do troubleshooting. Another really important feature where you can prevent these things is Blue Hill Universal Security, where you can predefine different user types. So you would set up somebody who's the administrator, who can then configure the test system. He can configure the whole security setup. And that person also can do basically everything from editing methods to testing specimens and so on. Then you can set up somebody who's like maybe the lab manager, who can then edit test methods and test specimens. And then you can set up different operators that then also have to log into the software, which then will give you a timestamp when different operators logged in. And then they're typically very limited to what they can do, probably just the standard inputs for specimen dimensions and then testing the specimens. And now also keep in mind, you can obviously combine this with the workflow that we showed earlier. So you're preventing operators from doing critical changes that might throw off your data, and at the same time prompt them through the testing with the workflow. Okay, now we're going to look at some random tips and tricks before we go into Q&A. So if you test extremely stiff materials, you typically need to have a higher extensometer class. Like if you have a very stiff unidirectional coupon that you're testing, it's most likely not going to strain very much. So if you use an extensometer of a lower class, the arrow might be too large for what you're actually trying to read. So think about, what am I testing and what do I actually need to achieve the right measurements? And then in general, are you really getting the right failure modes or not? If you are, you probably don't want to change very much or anything. But if you do, that's really like you're not getting the right breaks in the right section, or you have too many retests. You know, typically you see like 5 or 7 specimens in the testing standards that they say you should test. And if you have to retest 50%, like that's probably a sign to make some changes and see where you can improve your inconsistencies. It's also important to note that different testing standards will give you different results. For example, compressive strength, even if you're testing the same material. So if you're testing with ASTM D3641, and then you have a stress value for that, and then you do the same test for ASTM D3410 or ISO 14126, you should not necessarily expect the same compressive strength results. There are different load introductions into the specimens, and therefore also different results typically. So only compare the exact same test types to each other. Another easy and really, like this is really a good one to also check out yourself, is don't touch the cable of a clip-on extensometer during a test, because it will directly affect your strain measurements. And you can best test this with maybe a dummy specimen, or just when the extensometer is connected to your testing machine and you have it just laying there, and you look at the strain measurement, and then you move the cable a little bit and just look at the strain reading. It will definitely change. Along those lines, make sure that you keep vibrations to a minimum when you're running tests. So not just on the test frame that you're using itself. For example, we've seen cases where there was, for example, a dynamic machine. I mean, lab space is always very critical, right? Like everybody always wants to max out their lab space. So if you put a dynamic machine next to a static machine and then you're running a dynamic test, you might introduce vibrations during your static tests. And then obviously that data will be more likely to be inconsistent, or, if you're testing static and you don't have the dynamic machine running. So keep those things in mind. Some testing standards also have sections called specific recommendations, and you should very much follow them, is my recommendation, because there's great tips in there, and they are typically aimed at reducing inconsistencies. So it's not required, but it's very much recommended to follow those. In general, read every standard all the way through. There's a lot of very, very important information in there. You should also make sure that you provide a significant amount of material under stress, and therefore produce more statistically significant results. So make sure that you're actually testing enough material to get what you want to try to find out. Okay, so with that, I think we're going to see if we have a little bit time left for some questions and answers.
Well, thank you, Stephan and Ashley, so much for all your great information. I thought first I would go ahead and share the results from the poll, if you guys would like to see that. So first was the question about if they're currently using Instron testing systems. And so we have a lot of people who are, some using, not using those, and other companies being utilized. Question number 2 about the testing thermoset composites, thermoplastic composites, or both. And so we have a pretty good mix of those answers as well. And then most importantly, how do you pronounce this word DATA? And seems like data wins out, but a number of us do use that interchangeably. So thank you all so much for participating in the poll. We appreciate that. So we do have some questions for you that I will start you on. Question number 1 is, what is the recommended ratio to prevent buckling when testing compression?
Yeah, okay, that's a good question. It depends on the testing standard you're testing to, for sure. A lot of times the specimen is either, predefined, or it gives you some allowable ranges. But it's typically mentioned in there. There's not like one answer, like one direct answer to that. It really depends on what standard do you actually want to follow, right? Like that really kind of determines how your specimen has to look or what kind of ratio you need to use. It really varies between the different standards because the fixtures are different between the different standards, and then also there's typically some kind of variation between ASTM and ISO standards.
Thank you. Our next question, when talking about extensometry, what is a wire form and how does this affect slippage?
Yeah, wire form, I do believe that refers to how you basically the mechanism that you're using to attach it to the specimen. So I think it's basically what kind of clamp are you using, because you have like a knife edge basically is what we call it at Instron, which is the part of the extensometer that actually touches the specimen, and probably, you know, they call it knife edges because they kind of like they cut a little bit into it because they need to have some grip. And then the wire form, I think, should be the part on the other end that clamps against the specimen, basically creating the pressure for the extensometer, because the clip-on extensometers, they need to stick on there somehow, right? I think that's what the wire form is referencing. Ashley, do you have is that
Yeah,
also your understanding?
if you go to slide 25, there's actually a picture of a
Oh, yeah.
clip-on, and we can point out what the wire form is exactly. It's in the calibration section.
All right. There we go here, the metal end here.
Yeah, so your wire forms typically in a clip-on situation are interchangeable and have they're machined with a tension to them. So you'll have some wire forms that have a really tight tension, and that's for like really thin materials. And then you have some wire forms that have a notch in them for rounds. And typically, like in the handbooks of clip-ons, there will be an indication of like the thickness associated with the wire form. But as Stephan was saying, there's typically also that knife edge that holds onto the material. You just want to be careful. I know this is about composites, but if you're also doing like some kind of plastics testing, try not to like run that knife edge along the plastic dog bone because you could actually score it. That could possibly happen with whatever type of composite that you're testing with. But it's okay to use your fingers to pull those prongs out a little bit and then like easily install onto the specimen you're testing. So I hope
I think that's a good point, because then we're back to like damaging the specimen potentially, right? And it's kind of like similar to gripping pressure. You want to find the sweet spot of just enough pressure so that you don't have any extensometer slippage, but you also don't want it to cut too much into your specimen, because then you're gonna potentially, you know, start notching into the resin or maybe even break some fibers.
Thank you. Our next question, do you have video extensometers available for D6641?
Okay, so yeah, I mean, no is the answer. There is, as far as I know, no extensometer solution for ASTM D6641 that I'm aware of. It also, maybe for R&D purposes, you can maybe try to do that. You know, because then it probably is not as critical to completely follow the standard as much, because it's, you know, research and development. But if you follow it for quality control, I'm very confident that you have to use strain gauges actually to conform with the standard. Ashley mentioned this earlier in the presentation with the difference of the two strain gauges on both sides of the specimen for specifically that testing standard. They are not allowed to be more than 10% apart. So if you like your strain reading on the one side is more than 10% off from the other side, then you're actually introducing too much bending. And then, you know, if you do a video extensometer, you would have to do that from both sides. So you would need two to conform to that with the standard, and then also the accuracy of the video extensometer would be questionable. And it's a very narrow channel to look into. If we look at the fixture, actually, I'm going to try to jump there real quick because we're showing it here on this slide here. Okay, maybe not this one. Let's go
37.
for, yeah, there we go. Because you would also, the other thing is, So I've seen one variation of this actually where somebody tried this. So if you use the standard fixture, you can kind of see here, like the flat side of the specimen is actually on this side. That's where, so you would have to look here from the right to the left, and then on the other side, the opposite, to see the flat side of the specimen. That's what you would want for your strain reading. And the guiding column is actually right in the way. Like you wouldn't be able to look past it. I did see though that, for example, Wyoming Test Fixture, who's, you know, one popular maker for these test fixtures, they actually have a modified version of this specific fixture that's basically this duplicated with 4 columns, and then you have the specimen in the middle of it. Gotta kind of use your imagination here. I don't have the picture ready, but basically that allows you then to look at the flat side of the specimen freely without guiding columns in the way, and then somebody tried to do digital image correlation with that. But keep in mind, like if you follow the standard, the opening between the two, the top and the bottom surfaces here is, I believe, only 13 millimeters, or at least the gauge section of the specimen is only 13 millimeters as far as I remember. And that is, you know, obviously a very, very small area or length in that, in you know, the specimen is not very wide. So the area that you're looking at is very small, and therefore, you know, to get accurate results, there's more or less only strain gauges really. But again, if people do R&D, I've seen things like that, yes.
Thank you. Our next question we'll take is the measuring add-on included in the standard version of Blue Hill Universal, or does it require additional purchases?
Ashley, do you have a definite answer on that one? I think it's optional. I think it is an add-on, but I'm not 100% sure.
Yeah, I'm not 100% sure either. But yeah, we'll have to double check.
Sure, we can share whose question that was with you guys, and then if you want to reach out with more information. So we have time for one more question, and then we've passed our time together, but we'll do one more question. This presentation seemed to be directed towards static testing with great information to enhance accuracy of testing using screw-driven machines and displacement and strain control. However, do your hydraulic, pneumatic-driven machines, which are better for cyclic loading using force control, have these same options? I'm sorry, I didn't ask that last part very well. Do your hydraulic, pneumatic-driven machines, which are better, I guess, for cyclic loading using force control? Yes.
So there's no pneumatic-driven machines. It's either electromechanical or hydraulically driven. Pneumatic, we do offer grips that are operated, or where the force is basically pneumatic. Just to clarify that point in regards to Instron offerings. And we do make, like, I'm no expert, unfortunately, right now on the dynamic portfolio, but I do know that we do have both options. There's electromechanically driven and there's hydraulically driven dynamic machines. Which of those are better for cyclical? I'm sorry, I'm not going to be able to really confidently answer that. So I would recommend to follow up with.
The question's more of, do dynamic machines have the same options that we've been talking about for static?
Okay.
But that might be hard for us to answer because we're static applications engineers. So that's another one that we would have to follow up on. We'd have to follow up on that one too.
Okay. Well, you actually have a number of questions still. So what we'll do is we'll take your questions and we'll share them with the Instron team so that they can take a look at those and see if they can reach out or add some information to our email that's going to go out, because we do have an email. Someone did ask if we would be sharing the recording. And so as I mentioned earlier, there will be the recording link coming out in the next 48 hours. So you'll be able to watch this again and come up with more questions. I know that I'm sure Ashley or Stephan or any of their team would be happy to talk with you more about this. So we thank you so much for being here. Stephan and Ashley, thank you for sharing with us about data and testing and composites. We appreciate you being here, and thank you all for joining us, and we hope you have a great afternoon.